In this video, we'll look at 2015 H2 Physics Paper 2, Question 4. Let us have an overview of the question. From the question and the parts asked, it is obvious the question is a gravitation cum circular motion question, for which, in Part A, you are asked to determine the centripetal acceleration of Io. In Part B, you are given a second moon of Jupiter, and you're asked to explain why gravitational field strength of each moon has the same magnitude and direction as centripetal acceleration of the moon. For B Part 2, it is a calculation question in which you're asked to determine the ratio of the orbit of Io to the radius of the orbit of Amalthea. Let us look at 4A. As usual, we start identifying the keywords with this question. For this part, in 4A, you are told that for one of the moons for Jupiter, it takes 1.53 times 10 to the power 5 seconds to orbit Jupiter. That would be the period T. It has a radius of 4.22 times 10 to the power 5 kilometers. Note that the radius is given in kilometers. To work out the value later, we will need to remember to convert these kilometers to meters. You are asked to calculate the centripetal acceleration of Io. We know that centripetal acceleration can be written as r omega squared, and omega itself can be written as 2 pi over t. So this is a straightforward calculation in which we can just plug in the values. Just remember to convert that 4.22 times 10 to the power 5 kilometers to meters by multiplying 10 to the power 3, and working this on a calculator, you should get 0.7117 meter per second squared. That should be the answer. We are going to leave the answer in a few more significant figures, just in case we will need this value for calculation later. Now let us move on to Part B. For Part B, you are given that a second moon of Jupiter, called Amalthea, has a centripetal acceleration of 3.87 meter per second squared. For Part 1, you are asked to explain why the gravitational field strength at the position of each moon has the same magnitude and direction as the centripetal acceleration of the moon. To put it simply, you are asked to explain why G is equals to AC. Note that I've put in the vector notation here, as there is both the magnitude and direction to consider. Before we jump in to write the answer, we note that this question is actually easier if we were to show using equations. However, this is an explain why question, and hence a qualitative answer with clear explanation is expected. For this type of question, it is good for us to explore the explanation using equations first, and then use it as a guide to craft our explanation. Now this is a force question, and hence we should make a quick sketch of the free body diagram. Sketching the free body diagram, we have the force acting on the moon, and that is actually the gravitational force. There is only one force, and hence, by Newton's second law, we see that the gravitational force acting on the moon provides for the centripetal force that's causing the circular motion. Now, we want to show that G is equals to AC. Therefore, we can write Fg as mass of moon times G, while Fc can be written as mass of moon times the centripetal acceleration. The mass of the moon is common in both sides of the equation, and hence we can cancel that out, and that leaves us with G is equals to AC. We see we end up with this vector equation, whereby it not only shows that the magnitude of G is equals to the centripetal acceleration, but rather the direction of G is also in the same direction as the centripetal acceleration. Using this working as a guide, we can now craft our answer in prose to explain why the gravitational field strength is equal in magnitude and direction as the centripetal acceleration. and we have the following key points. There is only a single gravitational force that's acting on the Moon. Hence, by Newton's second law, the gravitational force by Jupiter provides for the centripetal force of the Moon. But note that the question requests not for the force, but for the gravitational field strength to be the same direction and magnitude as the centripetal acceleration of the Moon. Hence, the second point needs to link the force to the field. And we have the gravitational force on the Moon is given by the product of the mass of the Moon and the gravitational field strength at the position of the Moon. And the centripetal force is the product of the mass of the Moon and the centripetal acceleration of the Moon. Since both gravitational field strength and acceleration are vector quantities, the gravitational field strength is equal in magnitude and in same direction as the centripetal acceleration. We will now move on to B part 2, the last part of the question. In B part 2, we are asked to calculate the ratio of the radius of the orbits of Io to the radius of the orbits of Amalthea. So what we would need is actually a relationship between AC and R. From earlier, we have already been asked to explain why G is equals to AC. So we know that G is equals to AC. But the gravitational field strength at every point can also be written as Gm over R squared. This will actually be the relationship that links AC to R. From there, we can see that the radius of orbit is proportional to 1 over square root of the centripetal acceleration. Hence, the radius of the orbits of Io over the radius of the orbits of Amalthea can be written as the square root of the centripetal acceleration of Amalthea over the centripetal acceleration of Io. From earlier, we see that the question has given us that the centripetal acceleration of Amalthea is 3.87, and from earlier calculation, we have the centripetal acceleration of Io to be 0.7117, so putting it into the equation, that will give us 2.33 as the final answer. So this brings us to the end of question 4.